Hi guys! We are the Team Dapo.
I am Kharen.
I'm Arnulfo.
And I'm Cherish Mae.
We will discuss Chapter 7, which is the Discriminant Analysis. Discriminant analysis is like K-means clustering. It groups observation together into like values, but it has the ability to predict. This is the scenario for the Chapter 7. Hill runs a sport academy designed to help high school-aged athletes achieve their maximum athletic potential. On the boys' side of his academy, he focuses on 4 major sports: football, basketball, baseball, and hockey. Hill has developed an extensive dataset, and he is wondering if he can use past performance from some of his previous clients to predict prime sports for up-and-coming high school athletes. He hopes he can make a recommendation to each athlete to the sport in which they should most likely choose to specialize. By evaluating each athlete's performance across a battery of tests, Hill hopes we can help him figure out for which sport each athlete has the highest aptitude. Hill's objective is to examine young athletes and, based upon their performance across a number of metrics, help them decide which sport is the most prime for their specialized success. Thus, he recognizes as a limitation of this data mining exercise that he may not be able to use data to determine an athlete's best sport. Still, he has seen metrics and evaluations work in the past, and has seen that some of his previous athletes really were predisposed and that they were successful as they went on to specialize in that sport. Based on his industry experience, he has decided to go ahead with an experiment in mining data for athletic aptitude and has enlisted our help.
As for the second part of the methodology, the data understanding, every athlete that has enrolled at Hill's Academy over the past several years has taken battery tests, which tested for a number of athletic and personal traits. These tests had been administered on both boys and girls participating in different sports. We have decided with Hill that we will look at data only for boys. Hill has the benefit of knowing which of his former pupils have gone on to specialize in a single sport, and which sport it was for each of them. We gather the results of the batteries for all former clients who have gone on to specialize. Hill adds the sports each person personalized in. We have a dataset comprised of 493 observations containing the following attributes. The first one we have is age. This is the age in years. Participants range in from 13 to 19 years old at the time they took the battery test. Second one is strength. This is the participant's strength measured through a series of weightlifting exercises and recorded on a scale of 0 to 10. The next one is quickness. This is the participant's performance on a series of responsiveness tests. Injury. This is a simple yes or no column indicating whether or not the young athlete had already suffered an athletic-related injury that was severe enough to require surgery. Vision. Athletes were not only tested on the usual 20/20 vision scale using an eye chart, but were also tested using an eye tracking technology to see how well they will be able to pick up objects visually. Next one is endurance. Participants were subjected to an array of physical fitness, including running, calisthenics, aerobics, and cardiovascular exercise and distance swimming. Following the agility. This is the participant's score on a series of tests of their ability to move, twist, turn, jump, and change direction. Next one is decision making. This portion of the battery test, the athlete's process of deciding what to do in athletic situation. Athletes participated in simulation that tested their choices of whether or not to swing a bat, pass a ball, and move to a potentially advantageous location of playing surface. And the last one, for the attributes, is the prime sport. This attribute is the sport each of the 453 athletes went on to specialize in after they left Hill's Academy. This is the attribute Hill is hoping to be able to predict for his current clients. As we analyze and familiarize ourselves with this data, we realize that all of the attributes, with the exception of prime sports, are numeric. And as such, we could exclude prime sport and conduct a k-means clustering data mining exercise on the dataset. Doing this, we might be able to group individuals into one sports cluster or another based on the means for each of the attributes in the dataset. However, having the prime sport attributes give us the ability to use a different type of data mining model, the discriminant analysis.
For the data preparation, we need two datasets, which is the training data and the scoring data, to be executed in the rapid miner. Training data are simply datasets that have the known prediction attribute. For the observations in the training dataset, the outcome of the prediction attribute is already known. The prediction attribute is also sometimes referred to as the dependent attribute or variable or the target attribute. It is the thing you are trying to predict. Rapid Miner will ask to set this attribute to be the label when we build our model. Scoring data are the observations which have all the same attributes as the training dataset, with the exception of the prediction attribute. We can use the training dataset to allow Rapid Miner to evaluate the values of all our attributes in the context of the resulting prediction variable, in this case, prime sport, and then compare those values to the scoring data and predict the prime sport for each observation in the scoring dataset.
To begin with, we create a new process. Import the 2CSV file on your folder. First, the training. Name it also as training 7. Next is the scoring data file. Name it also as scoring 7. In order to easily differentiate between the two, let's start by renaming the retrieve operator for the training dataset that you drag and drop in your main process window. Right-click on this operator and select Rename. We know from our data preparation phase that we have some data that need to be fixed before we can mine this dataset. Specifically, you'll notice some inconsistencies in the decision-making attribute. Run our model and let's examine the metadata. This is the identifying inconsistent data in the decision-making attribute. While still in results perspective, switch to the data view radio button. Click on the column heading for the decision-making attribute. This will sort the attribute from the smallest to largest. In this view, we see that we have 3 observations with the scores smaller than 3. We need to handle these observations. Click again the decision-making attribute. This will resort to the attribute in descending order. We have some values that we need to be addressed. In this decision-making variable, it resorted in descending order. Switch back to the design perspective. Let's address this inconsistent data by removing them for our training dataset. We could set these inconsistent values to missing, then set missing values to another value, such as the mean, but in this instance, we don't really know what should have been in this variable. So changing this to the mean seems a bit arbitrary. Removing these inconsistencies means only removing 11 of our 493 observations, so rather than risk using bad data, we will simply remove them. To do this, add 2 filter examples, operator in a row to your string. Connect the tree. For the first filter examples, in the condition class, we select the attribute value filter, and for the parameter string, we type the decision making and for the filter example number 2, select the condition class as the attribute value filter, and then also decision making is to 100. This will reduce our training data set down to 482 observations. Run the model. Then, as you can see, the example set are 482 examples. In design perspective, use the search field in the operators tab to look for the discriminant. Locate the operator for linear discriminant analysis. Add this operator to your string. Connect it. The trap port on the LDA or the linear discriminant analysis operator indicates that this tool does expect to receive input from a training dataset, like the one we've provided. But despite this, we still have received 2 errors. As indicated by the black arrow, the first error is because of our prime sport attribute. It is the data type as a polynomial, and LDA likes attributes that are numeric. This is okay because the predictor attribute can have a polynomial data type, and their prime sport attribute is the one we want to predict. So this error will be resolved shortly. This is because it is related to the second error, which tells us that the LDA operator wants one of our attributes to designate it as a label. In Rapid Miner, the label is the attribute that you want to predict. At the time that we imported our dataset, we could have designated the prime sport attribute as a label, rather than as a nominal attribute. But it's very simple to change an attribute's role right in your string. Using the search field in the operators tab, search for an operator called the set rule. Add this to your stream, and then in the parameters area on the right side of the window, select prime sport in the name field. And in the target rule, select the label. We still have a warning, but you will see the errors have now disappeared at the bottom of the rapid minor window. With our inconsistent data removed and our errors resolved, we are now prepared to move on to the modeling. We now have a functional stream. Then, run the model and let us see what is the result. With the mode port connected to the rest port, Rapid Miner will generate discriminant analysis output for us. This is the quadratic discriminant model. The probabilities given in the results will total to 1. This is because at this stage of our discriminant analysis model, all that has been calculated is the likelihood of an observation landing in one of the 4 categories in our target attribute of the prime sport, because this is our training dataset. Rapid Miner can calculate these probabilities easily. Every observation is already classified. Football has a probability of 0.3237. If you refer back to the feed to the past execution, you will see that football as prime sport comprised 160 of our 493 observations. Thus, the probability of an observation having football is 160 over 493, or 0.3245. But in steps 3 and 4, we remove 11 observations that had inconsistent data in their decision-making attribute. 4 of these were football observations, so our football count dropped to 156 and our total count dropped to 482. 156 over 482 is equivalent to 0.3237. Since we have no observations where the value for the prime sport is missing, each possible value in prime sport will have some portion of the total count, and the sum of these portions will equal to 1, as is the case. These probabilities, coupled with the values for each attribute, will be used to predict the prime sport classification for each of Hill's current clients represented in our scoring dataset. Now, we go back to the design perspective, and in the repositories tab, drag the scoring dataset over and drop it in the main process window. Do not connect it to your existing stream, but rather allow it to connect directly to our REST port. Right-click the operator and rename it to scoring. Run the model again. Rapid Miner will give you an additional tab in Results Perspective this time, which will show the metadata for scoring dataset. The scoring dataset contains 1,184. However, as indicated by the black arrow in the range column of the figure, the decision-making attribute has some inconsistent data again. Repeating the process previously outlined in Steps 3 and Step 4, return to design perspective and use 2 consecutive. The filter examples operators to remove any observations that have values below 3 or above 100 in the decision-making attribute. This will leave us with 1,767 observations, and you can check this by running the model again. The example set are 1,767 observations. We now have just one step remaining to complete our model and predict the prime sport for the 1,767 boys represented in our scoring dataset. Return to the design perspective and use the search field in the Operators tab to locate an operator called Apply Model. Drag this operator over and place it in the scoring dataset stream, and then connect. As you can see, the apply model operator has given us an error. This is because the apply model operator expects the output of a model generation operator as its input. This is an easy fix because our LDA operator, which generated a model for us, has a mod port for its output. We simply need to disconnect the LDA's mod port from the rest ports it's currently connected to, and connect it instead to the apply models operator mood input port. To do this, click on the mood port for the LDA operator, and then click on the mood port for the apply model operator. this view is the discriminant analysis model with training and scoring data streams. We run the model, and then RapidMiner will generate 5 new attributes and add them to our results perspective. This is the prediction attributes generated by the RapidMiner. The first 4 attributes created by the RapidMiner are confidence percentages, which indicate the relative strength of RapidMiner's prediction when compared to the other values the software might have predicted for each observation. In this example dataset, RapidMiner has not generated confidence percentages for each of our 4 target sports. If RapidMiner had found some significant possibility that an observation might have more than one possible prime sport, it would have calculated the percent probability that the person represented by an observation will succeed in one sport and in the others. The phenomenon did not occur, however, in the datasets we use for these chapters. This is most likely explained by the fact discussed earlier in the chapter. All athletes will display some measure of aptitude in many sports, and so their battery test scores will likely be varied across the specialifications. In this statistical language, this is often referred to as heterogeneity. Not finding confidence percentages does not mean that our experiment has been a failure, however. The 5th new attribute generated by the RapidMiner when we applied our LDA model to our scoring data is the prediction of a prime sport for each of our 1,767 boys. As you can see in the data view, the RapidMiner has applied a discriminant analysis model to our scoring data, resulting in a predicted prime sport for each boy based on the specialization sport of previous academy attendees. This is how discriminant analysis occur or process.
For the deployment methodology, discriminant analysis has given Hill some idea about where his young proteges may have strength, and this can point him in certain directions when working with each of them. But he will inevitably gather more data and learn whether or not the use of this data mining methodology and approach is helpful in guiding his clients to a sport in which they might choose to specialize as they mature. For this chapter summary, discriminant analysis help us to cross the threshold between classification and prediction in data mining. Prior to this chapter, our data mining models and methodologies focus primarily on categorization of data. With discriminant analysis, we can take a process that is very similar in nature to k-means clustering, and with the right target attribute in a training dataset, generate data mining for the predictions for the scoring dataset. This can become a powerful addition to k-means models, giving us the ability to apply our clusters to other data that haven't yet been classified. Discriminant analysis can be useful where the classification for some observations is known and is not known for the others.